Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. We are going to continue with our final part in partial differential equation chapter where we are going to continue with parabolic partial differential equation or PDE. So a general second order linear PDE with two independent variables x and y given by a uxx plus b uxy plus c uyy plus d equal to 0, where we know that uxs is the second derivative of u over x, uxy is the second derivative of u over x and y, and uyy is the second derivative of u over y. A, b, c are the function of x and y, while d is a function of xy, u, ux, and uy. And this general equation will be parabolic if the b square minus 4ac is equal to 0. So this equation 1 is called as a parabolic partial differential equation, parabolic PDE. And one of the simple example of a parabolic PDE is the heat conduction equation for a metal rod, where alpha, second derivative of T over X, is equal to derivative of T over time, where T would be the temperature with the functions of location X and time T, in which the thermal deficit alpha is given by alpha equal to K rho C, where K is the thermal conductivity of the rod, rho is the density of the rod, and C would be the specific heat of the rod material. Parabolic equations are usually employed to characterize the time variable unsteady state problems. Conservation of energy can be used to develop an unsteady state energy balance for the differential element in a long or thin insulated rod. We are going to use the fully discrete methods to discretize in both time and the space dimension. So in a fully discrete finite difference method, we are going to replace the continuous domain of the equation by a discrete mesh of points. When we replace the derivative in the PDE by finite difference approximation, and we see a numerical solution that is a table approximate values at the selected points in the space and time. In two dimension, one space and one time dimension, the resulting approximate solution values represent points on the solution surface over the problem domain in the space-time plane. The accuracy of the approximate solution depends on the step size in both space and time. So in order to discretize the parabolic PDEs, we can have a thin insulated rod as shown here, where we use schematic diagrams to show the interior nodes inside the rod, where we have x dimension for the location, and also we have the t dimension for the spatial dimension, and we have a rod length of L, and we divide into n plus 1 nodes, and therefore we are going to have the delta x will be equal to L over n, where delta t would be the time steps, where similarly it will be broken into same time steps, and therefore we are going to get for tji, where j is for the times and I is for the location, correspond to the temperature at node I, that is x is equal to I times delta x, and the time t will be j times delta t. So this is how we are going to discretize the rod. So replacement of all partial derivative by finite differences result in a system of algebraic equation for the unknown solution at a discrete set of sample points. So we are going to get numbers of equations for the unknowns, and this system could be linear or nonlinear, where it depends on the PDE itself. With an initial value problems, where usually we have the value for t equal to 0 or the x equal to 0, the solution is obtained by beginning with the initial values along some boundary of the problem domain and marching forward in time step by step, generating successive rows in the solution table. Such a time stepping procedure may be explicit or implicit, and it's going to depend either the formula for the solution values at the next time step involve only past information. We would expect to obtain arbitrarily good accuracy by taking sufficiently small step size in the time and space, okay, the value of delta x and delta t, and the two step size cannot always be chosen independently for each other. However, For the approximate solution to converge the true solution of the PDE as the step size in time and space go to 0, we must meet two conditions, which is consistency and also the stability. For consistency, which means that the local truncation error goes to 0 as the step size go to 0. So, for example, the discrete problem approximate that the right continuous problem. For stability, we have seen in other contexts, it means that the approximate solution remains bounded. So we have to make sure that it is bounded, and specifically the global error is bounded by the constant times the is bounded by the constant times the local error. So based on what have been said by Lex equivalent theorem, consistency and stability are together necessary and sufficient for convergence. Neither condition alone is sufficient to guarantee a convergence. So we are going to take a look at one parabolic example. We have a thin insulated rod where one end is being heated and the other is cooled. So based on the heat equation where where dt, a function of x uh, and t, okay, location and time, over dt is equal to second derivative of t over dx. So we are given an initial condition of t0t, okay, where at location 0 at time t is equal to t1 t equal to 0, and tx0 at time 0 is equal to sine pi x. So this is going to be a parabolic problems when b square minus 4ac is equal to 0, and the boundary conditions are needed to uniquely specify a solution. So we are going to determine the boundary conditions. So from the energy balance together with the Fourier's law of heat conduction energy balance together with Fourier's law of heat conduction yields heat conduction equation, where we know k, second derivative of y over x, is equal to dt over t. So just as elliptic PDEs, the parabolic equations can be solved by substituting finite divided differences for the partial derivative. In contrast to elliptics, we must now consider changes in time as well as in the space, so x and t. Parabolic PDEs are temporally open-ended and involve new issues such as stability. So using finite difference methods, first we are going to divide the interval x into subinterval, each with width h, okay, same width. And we are going to divide the interval times t into subinterval with width k. And we are going to put a grid of points to be used for finite difference solutions, and we are going to use tij to represent txi tj, where x would be the location and t would be the time. Replace the derivatives by finite difference formulas. So this is going to be our grid. For solution, this is a grid where we are going to use for the finite difference solution of parabolic PDE in two independent variables such as the heat conduction equation. So note that in this grid, okay, unlike the elliptic PDE, this grid is open-ended in the temporal dimension. So it is open-ended in the time dimension. So previously we have it is closed-ended. Okay, so this is closed-ended for elliptics, but for parabolics it is open-ended for time. So it can go until infinite. So we are going to replace the derivative by finite difference formula, where the central difference formula for second derivative of t over x is given by second derivative of t over x approximately equal to ti minus 1 j minus 2 tij plus ti plus 1 j over x squared is equal to ti minus 1 j minus 2 tij plus ti plus 1 j over h squared, where we know that h is for the subintervals of x and K will be the subinterval for H. So we are going to replace delta X with H. And for the forward difference formula for dt over t, okay, for the second part of the equation here, okay, we are going to approximate it is equal to Tij plus 1 minus Tij over delta t, where we are going to replace delta t with K. And from here, we are going to present the solution using two different methods. Okay, the first one will be the explicit method, where we are going to assume a simple and stability problems. And the second method is by using a Crank-Nicolson method, where this method are going to involve the solution of a tri-diagonal system of equation and also stable. So let's take a look first at the explicit method. So using the explicit method, the heat conduction equation are going to require an approximation for the second derivative in space and the first derivative in times. So we are going to have first derivative of t over times and the second derivative of t over space, where we can replace the derivative with x t plus k, okay, the subinterval of times, minus t x t over k, where the second derivative is going to be equal to tx minus h, the subinterval in space, t minus 2txt plus tx plus h, t h squared. We can improvise this equation by placing the k to the left part, to the right part of the equation, where we are going to get k over h square is equal to tx minus ht minus 2txt plus tx plus ht, where we are going to define that lambda is equal to k over h squared. So this equation can be written for all the interior nodes on the road, and it then provides an explicit means to compute values for each node for a future time based on the present values at the node and its neighbors. So we have to notice that this approach is actually a manifestation of the Euler methods for solving system of the ODE. And that is if we know the temperature distribution as a function of position at an initial time, we can compute the distribution at a future time based on the equation that we have here, where tx t plus k is equal to lambda tx minus h t plus 1 minus 2 lambda times txt plus lambda tx plus ht. So how are we going to compute the equations for all the nodes? So by using this equation, okay, it means that for temperature at point x and at the time interval t plus k, okay, we can use the temperature at point at space x minus h times t at time t, and nodes at xt and node at x plus ht, okay, to provide the temperature for the future temperature for t plus k at time interval k. So t plus k can be computed directly using this equation. We can replace all the knowns and unknowns into this equation, but it can be unstable as errors are going to be magnified. And in order to guarantee the stability of the solution, okay, 1 minus 2 lambda should be larger than 0, where we should get lambda should be less than half, and k should be less than or equal to h squared over 2. And this means that k is much smaller than h and is going to make it slow. Convergence and the stability of the solution. So in order to confirm the convergence and the stability, for the convergence, the solution converged means that the solution obtained using the finite difference method approach the true solution, as the step for space delta x and times delta t should approach 0. And for stability, the algorithm should be stable if the errors at each stage of the computation are not magnified as the computation progresses. So we are going to look at the first example, okay, the heat equation using the same heat equation. We have a thin insulated rod with length x, where we have one part is being cold, chilled by ice. So using the heat equation, second derivative of u as a function of space and time minus first derivative of u over times. So this is actually equal to the equation that we have previously, where u we are given the initial condition where u at space at location 0 and times t is equal to u at location 1 time t is equal to 0, and ux0 will be signed by x. So we use the value of h is 0.25. Okay, the intervals in space, remember h is for delta x, and k for delta t is 0.25 also, to find the uxt for x 0, 1 and t 0, 1. So we are going to get the lambda will be equal to kh square, should be equal to 4. So using the same equation, okay, we can replace all the values that we have, h and k, okay, with the values that we get 0.25 and 4. So we should get the equation of uxt plus k equal to 4u x minus ht minus 7uxt plus 4u x plus ht. Okay, by drawing a schematic diagrams of the nodes inside the rod, okay, where we are going to have at the y-axis would be the temporal dimension from t0 to t1, t1, and the space dimension from x0 to x equal to 1. So we need to find, okay, the temperature. We know that at this part it is equal to 0. Okay, this is all equal to 0, and at this part it is all equal to 0 also, okay, from the initial condition, and at this part it is all equal to sine pi x. Okay, sine pi x. Okay, so we only have to determine 12 nodes that is inside, or the interior nodes inside the rod and inside the time interval. So let's start with the first node, okay, this node here, where we know that the node here is t0, t x0, t0, and here is x0.25, and the value for t is sine 0.25 pi, and the next is the right part will be sine 0.5 pi. So we can compute the value by substituting all the value that we have uh, for uh, for x and t, where we are going to get the value for u 0.25, okay, here would be minus 0.9497. Okay, so similarly we can do the same for the next node, okay, where this is node 0.5, 0.25. So we can just replace the values with the nodes from here, and we are going to obtain minus 0.1716. So on from this example, there are some remarks that we have to take notes. The first one is that the obtained results are probably not accurate, because we know that 1 minus 2 lambda, where lambda is equal to 4, okay, will be equal to minus 7. And for an accurate result, 1 minus 2 lambda, this value should be larger or equal to 0. So we get minus 7. So we need to select k, which is less than h squared over 2, which is the value for k should be less than or equal to 0.03125. So for example, we can choose the value of k is 0.025, okay, which is better, it is smaller than the one that we need. and the value for lambda then would be 0.4, and therefore we should get 1 minus 2 lambda would be equal to 0.2. Okay, and this is going to be larger than 0, and should get a more accurate result. So let's use the value that we have 0.025 k for the interval of the time. So we need to use we are going to change the value of k to 0.025, and using the same equation, okay, this time we are going to get the value for the first node here would be 0.5414. So take note that this value is much different from the one that we obtained using 0.25 for the interval of t. So this is negative 0.94. So there will be soft errors, okay, compared to the one that we have previously. And we can proceed with the second node, where we are going to get 0.5 and 0.025, okay, and we get the value as 0.7657. So note that the difference in the values when we change the value of k and h in order to get a more accurate result. So next we are going to proceed with the Crank-Nicholson method. The method involves solving a tridiagonal system of a linear equation, and this method is stable. We have no magnification of error, so we can use larger value of h and k compared to the explicit method, where we need to minimize, or we need to use much more smaller value of h or k. So based on the finite difference method, we are going to divide the interval x into subinterval with h. So this is for delta x, and the interval t with k. This is for delta t. Replace the first and second partial derivative with their backward and central difference formulas respectively. So we are going to get the same formula. So second derivative of u over space, and the first derivative of u over times, we are going to get ux minus ht minus 2uxt plus ux plus ht over h squared. And our heat equations, okay, are going to becomes like this. Okay, ux minus ht minus 2uxt plus ux plus ht. So we know that x minus h, x plus h will be next to each other, where x will be in between, and uxt minus uxt plus k over k. In the next part, we are going to obtain k minus kh square, where we know this is minus lambda, plus 1 plus 2k h square. So this is can also be replaced with lambda, minus kh square, this is also for lambda, is equal to uxt minus k. So we should get this equation, okay, by defining lambda equal to kh square. We are going to get negative lambda u plus 1 plus 2 lambda uxt minus lambda ux plus ht equal to uxt minus k. So this time we are going to get uxt minus k, okay, based from the temperature or the nodes from the x minus ht, xt, and x plus ht. So the equation can be rewritten as minus lambda u I minus 1j plus I plus 2 lambda uij. So I is for the space and j is for the time, minus lambda ui plus 1j equal to ui j minus 1. So we can expand as a system of equation where we are going to fix j equal to 1, okay, where j is equal to 1. So we should get the time is start from t equal to 0, where negative lambda u01 plus 1 plus 2 lambda u11 minus lambda u21 is equal to u10. Okay, for u20, u30, u40, okay, we are going to get the equation accordingly. So we can express the equation as a tri-diagonal system of equation, okay, where we are going to get a matrix of 4 times 4. Okay, we have 4 nodes here. So we can replace the equation into matrix 1 minus 2 lambda minus lambda minus lambda 1 plus 2 lambda minus h minus lambda 1 plus 2 lambda minus lambda minus lambda 1 plus 2 lambda, and the unknowns for the nodes u11, u21, u31, and u41, where u10, 20, 30, and 40 will be the initial temperature value, okay, at time t equal to 0, and at x equal to x0 plus h, x0 plus 2h, and x0 plus 3h, and x0 plus 4h. So this will be the initial temperature value, and we are going to use the boundary values for x equal to x0 and x0 plus 5h is equal to u01 and u51. So the solution of the tri-diagonal system are going to produce the temperature values for u11, u21, u31, and u41 at the time t equal to t0 plus k. And in order to compute the temperature values at t equal to t0 plus 2k, what we have to do is we have to just change the value of j equal to 2. So we can just replace from the previous equation 1. Okay, we can change to 2. And to compute u12, u22, 32, and 42, we are going to repeat the above step, okay, for temperature values at T0 plus 3K, okay, where J will be equal to 3, and so on and so forth. So we are going to solve the PDE for the heat equation, where we have U at space 0 times T equal to U1 T equal to 0. So we have the boundary condition is 0 at the beginnings. So x equal to 0 and x equal to 1. So we have all this is equal to 0. And we also have u x0 equal to sine pi x. So x0 will be sine pi x. Okay, similar like the example 1. So this time we are going to use Crank-Nicholson method, where we are going to use the value of h is 0.25 and 0 for k is 0.25 also. So this is for delta s and delta t, and we need to find the value for u at x and t from 0 to t1. Okay, so using the equation that we have obtained previously, we can replace all the value of h and k. Okay, and we should get this equation: 16u minus 2u plus u minus 4 equal to 0. And we are going to define lambda is equal to kh square, where we are going to obtain lambda is equal to 4. And we can replace x minus h with I minus 1 and t with j. So we get this equation: minus 4u plus 9uij minus 4ui plus 1 equal to uj minus 1. So we are going to start with j equal to 1, so that we can use the boundary condition t equal to 0. Okay, using j equal to 1, okay, we can obtain these three equations, okay, for this node, the first node, okay, where we get sine pi over 4, and the second one we get sine pi over 2, and the third one we get sine 3 pi over 4. And from these three equation, we can solve this equation using matrix by using any software, MATLAB, or your just simple calculator, to obtain the value of u11, u21, and u31. Okay, so this will be the value for this part here, 21, and u31, this one. We are going to obtain the value for u11 is 0.2, U21 is 0.29 and U31 is 0.21151. Okay, for the second row, this point, okay, we are going to proceed with the same equation. Okay, and by replacing all the values that we have, we are going to get this equation. We are going to get this value for the first equation, second and third. And this is when second row, when j is equal to 2. Okay, we use matrix and we are going to obtain by inversing the matrix and multiply by the value of the equation. We should get the value of the nodes at U12, U22 and U32 as shown here. Similarly, we can continue with the third row. Okay, the third row here. Okay, and the fourth row, and we can proceed with the second column where x is equal to 0.5. Okay, and we can start again from t 0.25, 0.5, 0.75 and so on. So as a remarks, explicit method, we are going to need to use a small value of k to ensure the stability of the solution. The computation per point is very simple, but many points are needed to solve one point. But for Crank-Nicolson method, we are going to require the solution of a tri-diagonal system. It is much more stable as larger k can be used. Okay, we can use larger k. And I think that's it for parabolic PDE. Okay, we just have two different methods that we can use to solve a parabolic equation. One is explicit and another one is a Crank-Nicolson method. And the rest will be the same like elliptic, where we just form some equations and form matrix to solve the value for the interior nodes that we need to find. Okay, that's it for our lecture. Thank you very much.